Slope is the ratio of the vertical change to the horizontal change between any 2 points on a line. So given two coordinates, like A and B, which you might recognize from the previous set of notes, given these 2 points, we should be able to calculate the steepness of the line that we have there. All right, now let me talk a little bit about what numbers we would expect for steepness. Okay, suppose that we had a perfectly horizontal line. That is going to have a steepness of 0. It has no slope. It just, no steepness at all. It doesn't go up, doesn't go down. Okay, so that would be a 0. When it tilts in this direction, okay, so I'm trying to keep it stuck on that point there. When I tilt it like that, this creates a positive slope. If I tilt it this way, that will give me a negative slope. So it's almost like a hill is going down versus a hill that is going up. All right, when you get, let's see here, so that's at 0. When you get to perfectly vertical, you've kind of maxed out on your steepness, because once you go past that point, you're now more in a negative direction there. All right, when you are at perfectly vertical, that is undefined, you actually have an infinite steepness at that spot. You can't even quantify it because it's so steep, so we call that one undefined. All right, now if you go halfway between horizontal and vertical, which is this, I always call it the perfect diagonal, it goes diagonally across all these boxes here, that would be a slope of 1. Okay, anything below that into the horizontal is going to be from 0 to 1, so they're all like fractional amounts. Anything from 1 up to the vertical, those are constantly increasing all the way up to an infinite steepness. It's kind of crazy that on one half you've only got 1 to 0, and then above 1 you've got all the way up to infinity. All right, so let's talk about what the definition says. Slope is a ratio. A ratio, simply put in math class, is a fraction. Yes, it's a comparison of two numbers, but the way that we always mathematically deal with a ratio is in a fractional form. So we're thinking of a fraction that has the vertical change to the horizontal. That means that the vertical change is going to be the numerator, the horizontal change is going to be the denominator. Okay, so like when we worked with distance, it was important to see the horizontal and the vertical components. Okay, how do I go from here to there? You can describe it horizontally as going 6 units to the right and then going up 8 units vertically. So that is the vertical change and that's the horizontal change, which means that the slope between these 2 points is 8 over 6, or 8 to 6, which does reduce. We always want to reduce these if we can. You can reduce that to 4/3. That has a slope of 4/3. Now, not that we normally do this, because we definitely like slope in fraction form, but if I divide 4 by 3, of course, you'll see that that's greater than 1. It's 1 point repeating 3, so let me go back to at least one thing I'd shown before. The perfect diagonal, so if I go right diagonal across each of these squares, that would be a slope of 1. So you're going to see that that's greater than 1 at 1.33. It's steeper than that. And that's what slope is. It's just figure out a vertical change, compare it to the horizontal change, and that's it. Oh, remember from midpoint with these two coordinates, that was the midpoint, and it was a true coordinate at -1, 6. So look what happens if we count from here to there. You've got 1, 2, 3, 1, 2, 3, 4. So vertical change of 4, horizontal 3, 4/3. It's just the reduced answer, the same one that we got. So that goes back to the definition where it says that it can be between any 2 points on the line. It's just if the points are further apart, you'd need to reduce it. If the points are as close together as we can get them, that will be your reduced answer. This is our slope formula. You're going to see that we have the letter m here. M is equal to, m is the typical variable that we use for slope. Not really sure where the choice for that one comes from, but it is m. That's the one that we end up using. What you'll see here is, yeah, it's a fraction. You have a numerator and you have a denominator, and the numerator is the changes in the y values, because the y values contribute to the height of the coordinates, which will then be your vertical change. The bottom, the denominator, is going to have your x's on there, and that's going to help give you the horizontal change. So it is the ratio that compares the vertical change to the horizontal. Notice that we do have subtraction in here, because you want to take, say, the height of one coordinate, subtract the height of the other one, and then that'll give you the space that's between them, which in our previous problem was the 8. You also want to be able to subtract your x's to get the space between them, which is 6. At least it was 6 in the last one. For this, you do want to be very, very careful that you don't mix up the coordinates that you're using. Make sure that you know what is your coordinate 2 and what is your coordinate 1, because if you've got the top written in a certain order, but the bottom gets flip-flopped here, then your answer ends up just being the opposite of the correct answer, and that means that it will be negative when it should be positive, or positive when it should be negative. All right, so in example number 2, we're going to do the basic evaluating problem. Let's figure out the slope of the line that would pass through these 2 points here. Okay, so what I have to the left is going to be me using the actual formula. To the right, what I'm going to do is demonstrate the method that I usually go about with this stuff. Okay, but so the formula is not a bad thing here. Okay, I know when I talked about distance formulas, like the thing is just so big and there's a lot of extra steps in there that you could just sort of get around by knowing Pythagorean theorem. For this, it's not that big. It's fairly user-friendly, if you want. The only thing that you need to make sure you do is that you subtract in the right order. So on the top, and remember that the top has to be the y values, the bottom has to be x. Don't mix that up. It's incredibly important. Do not mix that up. All right, so on the top, I have 2 minus -1. So that means is I took the first coordinate and subtracted the second one from it. So that's the order I'm doing. I'm subtracting this way. Okay, and of course, 2 minus a negative number is going to be 2 plus. The number says 2 plus 1 gives you 3. Okay, but remember that I went in this order. I subtracted that way. So the bottom needs to be with the x's 5 minus 4. You got to be very careful that you don't switch the order on there. So it is 5 minus 4, which gives you 1. The slope is going to be equal to 3 over 1, which of course is the same thing as 3. Now, a little bit of side note here. You can just state the slope is 3. If you need to graph, this ends up being a little bit more helpful because it tells you from point to point that you're going to have to go up 3 points and then over 1 point. You don't quite see that when you have the number written that way, but know that these are the same thing. So if you're trying to take a slope and graph it, remember that you can put a 1 underneath it, and then that tells you that horizontal change. This does not mean you just keep going up 3, up 3, up 3 forever. That's not, it's up 3 and over 1. All right, my method at how I approach this looks somewhat like what I did with the distance formula, but I have a very strict rule at the beginning. Very strict rule here is that when I do a comparison, I'm going to start with my y values and I'm going to draw this thing on top. So this is how I do it. Okay, I got my 2 coordinates and I'm going to draw a little bar that connects the 2 to the -1 because those are my y values. And I'm going to want to figure out what the distance is between these. But at the same time, I want to know what direction that I'm going, because slope is really dependent on like whether it's going up or it's going down, like all those things to consider. So we want to keep that in mind as well. And just ask ourselves the question, how do I get from 2 to -1? Well, to get there, I have to subtract 3. Got to subtract 3 to get there. Now over here, you see it as like a +3, but it's all going to work itself out. Okay, so how do I get from 2 to -1? I subtract 3. And I put that on top because when you calculate slope, you need to have your y values on top. So I always make sure I do the y's on top. And then on the bottom, I'm going to do my x's. And again, I'm going to ask the question, how do I get from 5 to 4? I'm not just asking about the space between them, but I'm asking the question, how do I get from 5 to 4? In fact, let me draw these little arrows to help indicate that. How do I get from 5 to 4? I have to subtract 1. And that is the slope. It's sort of done. Like all the numbers are there. The only thing that we notice is like, oh, there's 2 negatives, so the negatives are going to cancel out, which will leave us with just 3, the same thing that we get there. Okay, so both methods are good. Not going to discourage you from using this one, and it's good to know how that is done. But this is something that you can use if you want as well. Just remember, it's about how do we get from one number to the other. It's not just the space that's between them. Because when we did distance and I talked about Pythagorean theorem, I could just talk about it as space because I knew the numbers would get squared and they'd become positive anyway. But here it is really important that we know the direction, whether we're adding or subtracting. All right, so next we're going to look at parallel and perpendicular lines. Both of these types of lines have something very interesting about their slopes. So with parallel lines, you're going to have 2 or more. You can have a whole lot of them. And they all have something in common with their slopes. Perpendicular lines is only going to be 2. They're going to be 2 lines that meet at a right angle, and they also have something interesting about their slopes. So we're going to start with graphing this line, y equals 3/5 x plus 4. We're also going to graph a line that's parallel to it that happens to be going through the origin. Okay, and what we're going to do is eventually compare the slopes that we have here. So we want to complete the statement here. The slopes of parallel lines are blank. Okay, so let's start with just getting that graphed. Okay, things I hope you remember. This is what we call slope-intercept form. That's how this is structured. It's this right here, y equals mx plus b. That's slope-intercept form. The constant that we have at the end is going to be the y-intercept. That would be where it's crossing the y-axis. So this is going to cross at 1, 2, 3, 4. Going to cross there, and then m is your slope, which I had mentioned a little earlier in the formula. Okay, so m is going to tell you the vertical and the horizontal changes. And now we're going to actually use the slope to graph it. So the 3 tells us that from this point we need to go up 3 units, 1, 2, 3. The 5 is going to tell us that we got to go to the right 5 units. So you go 1, 2, 3, 1, 2, 3, 4, 5. Okay, so that'd be another point. And then you can continue the pattern, which is always a good idea so you can get a really good picture of the graph. You can go up another 3 and then go over 5. So that one barely fits with the second coordinate, but you know, you want to make as many coordinates as you can because that'll give you a better graph. If the tilt of your ruler is slightly off between just the 2, then it gets further and further off later. So plot as many as you can. Okay, that is this line. And now what we want is one that is parallel to that one and going through the origin. The origin, of course, is at 0, 0. If I were to place the ruler right here, I could actually draw a line that goes right there, and that would be parallel to it. Unfortunately, that doesn't go through the origin. I needed to actually pass through the origin. So I can kind of ballpark it if I want, and then get to that spot and draw it, right? But if, as I'm moving that, if one side moves a little bit more than the other one, I'll exaggerate it here. If it moves too far, you can tell that eventually my line will cross that one. Same thing can happen if I tilt it too much that direction. Okay, again, exaggerated, I wouldn't actually do that, but eventually it would cross there. So we really want it to be on the money. We do it. So I'm going to start looking at the coordinates now. And say, all right, let this coordinate sort of match up to the one that I would need at the origin. All right, let's look at those two, and they got a difference of 4 units here. Okay, and what they can kind of tell us is if those 2 dots are 4 units apart, then any dots that I have on my line should be 4 units apart from the line that's directly underneath it. Because if it isn't, then the line's going to get further apart, or it might be getting closer together, and that's not what's going to work. So let's take a look at this coordinate, right? Just count down 1, 2, 3, 4, and say it needs to be there. I need that space to be the same as this space and the same as this space right here, because if they're not, then the lines are eventually going to make contact. And that will give you a parallel line. And as you're doing that, this is kind of interesting, but as you're doing that, you may end up figuring out the answer to the question itself, right? If I just take these two dots and I move them the same distance down, then I look at the slope is still the same thing, right? Originally it was up 3/5, and then for this one, because the dots moved exactly the same amount down, you're still looking at up 3/5, okay? So the slopes of parallel lines are equal. You could say same, but because the slope is a numerical value, it works a little bit better just to say that they are equal, okay? So let's see what happens with perpendicular lines. We're going to graph this. This is y equals 3/2x. Okay, we don't have a constant on there, which means you can imagine it saying like plus 0. So that actually means that the line is going through the origin, right? If you don't have a plus number or a minus number, then you're just going to sit it at the middle. Okay, so from here, to graph 2 next point, we're going to go up 3/2. We'll go up 3/2, up 3/2. Again, do that as many times as you can that would fit on the graph, and there you are. All right, and that is our first line. The next, what we want to do is make one that is perpendicular to this and also intersecting at the origin. So we're still going to place it here and have it intersect at the origin. All right, now this one's going to be a bit of a tricky one. There's a couple approaches that you can take with it. Okay, there's a couple approaches you can take with it. One of them is you can actually just fold. You could fold the graph over onto itself, making a crease right there. If you do, when it folds over, you will get a perpendicular crease to this. So we can do that. I don't think with the paper that I have right now that's a good approach at it. So I have an alternative, which is to get a piece of paper or some other item that you know to be at a right angle. Okay, so this is a piece of cardstock paper. It's a little bit thicker than regular paper. It's a cut-off piece, but this was the original corner to the piece of paper they got. So I believe that is 90 degrees, okay? As absolutely close to 90 degrees as I can get. So what I'm gonna do with that is I'm gonna line it up. So it's really important that my first line was good, and I made all those little dots to go along with it. What I'm gonna do is I'm gonna slide it along, and anywhere I see that edge, that's a perpendicular. But I want it right at the origin. Okay, so I'm gonna take a little bit of time to make sure I'm like exactly where I want it to be. And then I'm gonna draw that. Okay, so that's my perpendicular. Now what we need to do is start to look at it and try and find a point that actually crosses at a nice coordinate. Okay, like when I'm looking at the line over here, that wouldn't be a good spot, these wouldn't be in good spots, and then finally I get like a coordinate. I get a nice spot that's right there, and then it picks up again like a duplicate later, right? So over 2, up 3, over 2, up 3, over 2, up 3. So I want to see something like that. Okay, so now I'm looking at, let me see, where am I? I got lost with all these little lines here. Okay, so that doesn't look like a true coordinate. That doesn't look like a true coordinate, right? Those are off, those are off. And right there, that looks pretty good. Okay, now I'm gonna mark it because I already know that is what I'm looking for. But what you should do is look at the pattern that we have here. So I'm going over 3 and up 2 and see if that pattern holds for the next one. So I go over 3 and I go up 2, and look, it still appears to be right on a coordinate. And if I go 3 and 2, it appears to be on that coordinate as well. So it looks like 3 in a row with the line that I drew seems to be fitting. So if you had a bad spot here, like it really wasn't a true coordinate, and you start repeating the pattern, you'll realize that your dots are getting further and further away from the line. They're gonna be more space. So the fact that we got 3 of them that seem to be on the line tells us that we're in good shape, and that's probably what we wanted. So now, let's take a look at our slopes. The slope that we had for the first is 3 over 2, up 3 and over 2. Both of those numbers positive, right? Up and right, up and right. Okay, now we look at the line that we have over here, the vertical. Okay, so we're going to treat it like the fraction. The vertical is going up 2. Yeah, so you got an up 2 here. And you've got a 3 for the horizontal. But if you take a look at the slopes, just step back, get away from the numbers here. This, as I mentioned, was positive, right? Both numbers are up and over. Over here, that's not really true. This actually has a slope that's negative. Now, it can come from either of these numbers. Okay, if I treat this as a positive 2 up, that means that I'm sort of looking like I'm going that direction. So I go up 2 units, but my horizontal is actually a negative 3. So it would be 2 over negative 3 because I have to go negative 3 and an up 2. Now, if I go left to right between points, this is going to have me go down 2 and to the right 3. So either way you look at it, it is going to turn out to be a negative slope. We get negative 2/3. I'm going to fix that because it doesn't look nice all spaced apart. All right, now what we're going to do is a comparison of these two numbers. They're the same values, but there's two differences. This is a positive slope. This is a negative slope. That's the first difference. The other one is that the numbers are upside down. They're actually reciprocals of each other. When the fractions are flipped, we call them reciprocals. So there's two things that we figured out. We first figured out that the slopes of the perpendicular lines would be opposite signs. One would be positive and one would be negative. The second thing that we figured out is that they were reciprocals of each other. So those end up being the two blanks here that we need to fill in. The slopes of perpendicular lines are opposites, reciprocals. All right, now the word opposite in mathematics is supposed to be reserved for positive versus negative. We use it for lots of other things, but ultimately that's really what it's supposed to be. So it fits perfect here. There's two things that you're always going to be looking for perpendicular. They do need to be opposites, and they also have to be reciprocals. If you just have opposites, that doesn't really mean anything. If you just have reciprocals, it doesn't really mean anything either. All right, example number 4. We're given 3 lines, A, B, and C, and we're asked to figure out which of these lines, if any of them are parallel or perpendicular. So you could have all 3 of them being parallel. You could have a couple of them being perpendicular and the other one being nothing. They can't all be perpendicular to each other. You can maybe have 2 of them perpendicular and then the third's parallel to the others, or one of the others. But to figure it out, what we need to look at is their slopes. That's what ultimately this all comes down to. Okay, let's take a look at line A. We've got y is equal to 5x minus 3. Okay, this is in slope-intercept form, which means that we have our slope right there. That's your freebie. Now, what do we do with the negative 3? Nothing. It doesn't matter. The positioning, like the location, whether the graph is higher or lower, it doesn't really matter in how it makes contact with the other ones. It's all about the tilt to it, which the tilt is going to be coming from the slope. So all we need are the slopes. Don't worry about the other things. All right, we take a look at line B. This is not in slope-intercept form, but it can quickly be moved into slope-intercept form, okay? Slope-intercept form does want you to have the y value by itself. So just kind of work on moving everything away from the y. So right now we've got an x plus 5y all together, but all we want is the y. So what we'll do is go ahead and move that x over by subtracting it. So that's going to give us 5y. 5y is equal to negative x plus 2. Okay, so the x gets subtracted, which is going to make it show up as a negative x on the other side. Okay, now to finish it, we still need to get rid of the 5. So we're going to divide everything by 5, which means that you got to divide this entire side by 5. So the 5 is going to go to the x part. It's also going to go to the 2. These, of course, will cancel. So we end up with 5 is equal to negative x over 5 plus 2 over 5 It just distributes to both of the terms that we have here. However, we don't really care about this one. I mean, it's not a really good y-intercept if you had to graph it, but for our purposes, we're only looking at the slope. The slope is right here. It's all of this stuff. That means that your slope is going to be -1/5. Okay, line C, we're going to need to rewrite that one as well. We're going to start by taking that -2x and moving it over. So that's going to give us -10y is equal to a +2x. You have to add it on, so it's going to go over there as a +2x. Okay, we had a 0, so you don't have any extra numbers that would be behind it. We're next going to divide by the -10. And we get y is equal to 2x over -10. Now, you don't normally write it that way, but I'm trying to just kind of keep it fitting with kind of generic approaches, not cleaning things up much. Okay, but this is going to be the slope. It's going to be the coefficient of the x, and it's also going to be that denominator, which is 2 over -10. That's the same thing, just as -2/10. That negative can just be moved out to the front. So you got -2/10, -2/10, which will reduce down to -1/5 for that slope. So now that we have all the slopes, we're going to make some comparisons here. These two, they're parallel. They got the same slope as each other. So B and C are going to be parallel. That's one answer. Let's see if we got anything else. So B is parallel to C. This is the symbol for parallel. You just got two vertical lines side by side. Most of our symbols in geometry look exactly like what they actually are, so that you draw parallel lines between them. So B is parallel to C. Okay, but let's see what else we got here. If we took this, same as that one, if we took this guy and we applied both of these changes to it, does it become 5? Okay, so if I made it its opposite, that means that it would need to be positive, and that's positive. Okay, so that part is true. Is it the reciprocal? Well, if you flip 5 and the 1 over, you get 5 over 1, which is the same thing as 5. So it ends up that this is actually perpendicular to A. Okay, so A is perpendicular to B. That's the symbol for perpendicular. Again, looks exactly like what it would be. It should be like a little right angle type shape there. But if A is perpendicular to B and B is parallel to C, then A must also be perpendicular to C.
Wait, there was.